Hello. So, um, so I hope everyone has been able to join the seminar. I hope everyone can hear me and see me well. So today's seminar is going to be in English by general petition. So we have to do certain seminars in English so everyone can obtain the credits in English and understand the seminar. So we'll try to do a few in Spanish and then try to make most of them in English so that everyone can follow them easily. So today's speaker, so our invited speaker today is Sergio Morales Tejera. He's a second-year theoretical physics PhD student at the IFT, so it's the Institute of Theoretical Physics in Madrid, which is associated to the CSIC, so what would be the Advanced Scientific Research Council here in Spain. He is originally from Tenerife, and he studied, or he did his undergraduate studies at University of La Laguna in Canarias. He has obtained an excellent award for Best Academic Record of the Year, and then he came to Madrid to study his master thesis in the IFT. Afterwards, he was offered to stay at the IFT to conduct his PhD research, which is what he's doing right now, and what he's going to tell us and talk about today in his seminar. So he's going to tell us about anomaly-induced transport via holography. For those of you who are not physicists, probably this is quite an hard title, but basically he's promised me he will try to make it as accessible as possible for everyone to understand, and it's just to get the main ideas straight. So without further ado, Sergio, if you would like to start, I will just close my camera and leave you to it.
Okay, so thank you very much, Valle, and thank you, the organizers in general. As Valle said, I'm going to talk about anomaly-induced transport via holography. I know the title can be a bit frightening, especially if you're not familiarized, if you're not a physicist, but I'm going to try to make sense of this title, and I will try to go from the very basic and give some take-home messages, okay? So don't worry. I will first talk about the physics of the problem, which is the anomaly-induced transport, and all the caveats or all the considerations in within. Then I will talk about the mathematical tool we have to tackle this problem, which is holography, which is the best part for me. And then I will try to explain how to combine both to model time transport in holography, and then I will show briefly some results, etc. Okay. But before that, let me talk about the Quark Gluon plasma, which is the system of interest, the physical system we're trying to model. So first of all, we all know from kindergarten that matter all around us is formed out of atoms. These atoms have electrons orbiting around some nucleus. These nucleus are formed at the time of protons and neutrons. And what you might not know is that electrons are fundamental particles, but protons and neutrons are not, in the sense that they are formed or they are composed by smaller particles. And these are quarks and gluons. Quarks are matter particles. They are just like electrons, if you want. And the gluons are interaction particles. What we call here, if we zoom in, this would be a nucleon, say a proton. These quarks and then the gluons interacting, they are similar to the photons in this context. Now, what happens to nuclei, for instance, and you accelerate them very, very fast, and you make them, is, of course, there will be, this is what they do at the LHC, they will produce a lot of particles and a lot of stuff that at the moment we don't care about. But the thing is that just
Sergio, sorry for interrupting you. I think there's been some problem of noise with your microphone.
really.
Um,
But can you hear me now?
maybe you're too near? You're too near the microphone. Maybe
I
can you put it farther away?
It's the microphone of the computer. I don't know. But can you hear me now?
So maybe if you just put the computer a little bit farther away from you.
Okay. Wait a second.
You don't have any headset or anything, or like headphones or something?
Sorry. I
Do
have.
you have any
I mean, the microphone is.
head
I
do you
have
have any
headphones
headphones?
here. Yes, I have headphones. Do
Maybe
you want me to put them on?
maybe we can try that, yeah?
Okay. Wait a second.
Okay, sorry for this. Let's see if we can hear him better with the headset.
Okay, now. Do you hear me now?
Yes.
Or not?
Yeah. We can hear you all the time. It's just that when you were using your computer's microphone, there was a lot of noise. So
Yeah, but now there is
can
no
you try
noise.
speaking now?
Yes, I'm speaking
Apparently
now. Much
yes.
better.
Apparently yes.
Okay.
Yeah. Okay.
Thank you.
Sorry, Sergio.
Uh,
So just continue.
just
Sorry.
one question. Where did you lose me? From the very beginning?
No, we were hearing you all through. It's just that there was noise, so it was annoying to hear. That's all.
Okay. I'll resume them. Uh, here I am. Okay. So as I was just saying, if you take these nucleons and you accelerate it very near the speed of light and you make them collide, then you will get a lot of stuff, but at the very early stages of this process, you will get a new state of matter. And this is the Quark Gluon plasma, and it's essentially that the nucleons at very high energies, very high temperatures, they just break and enter this state of matter. And what we are doing in this project is are studying a phenomenon, actually the chiral anomaly induced transport that is produced in this material. And this is also relevant for the very early time cosmology, because the universe right after the Big Bang had a phase which was dominated by this state of matter. Okay, so this is the physical system we need to have in mind. And now let's get a bit into the theory. I will try to explain to you what are these anomalies I am talking about. So first of all, you should know that in physics, symmetries are very important. At the beginning of physics, say, symmetries were regarded as some useful tool that could be used to simplify your problem. The perspective started to change a bit later, and symmetries acquired a very major role, and they are used now to construct our theories. Okay, so the thing is that in physics, asymmetry has an associated conserved quantity. This comes by another theorem. And how do we know that we have a symmetry here? Well, to describe a system with physicists and maybe also some engineers and mathematicians, we use a mathematical object that is called Lagrangian. So if we have a transformation that leaves this Lagrangian invariant, then we say we have a symmetry. Okay? Now, all this business is classical. But what happens if we want to include quantum mechanics into the game? Well, two things may happen. Either the symmetry is still there and nothing new happens, the symmetry is real, or the symmetry is broken by quantum effects. Okay, and in this second case is where what we call the symmetry is anomalous. Okay, Mathematically, this is very easy to see because, okay, here we have the Lagrangian. The Lagrangian will be still invariant under this symmetry, but in quantum mechanics, we need a more complicated object to describe the system, not just the Lagrangian. And this object is in the path integral formulation, is this partition function here that contains this extra bit. And it may happen that this extra bit is not invariant. Okay, so these are both points of view, intuitively and mathematically. The thing is that if we have a symmetry, a classical symmetry that is not a quantum symmetry, then the symmetry is anomalous. And this symmetry is this anomalous symmetry are the ones that are going to give us some transport in the material. We will come to that later. Okay. And now a small example that is the one of interest to us, which is that of the chiral symmetry, chiral transformation. Just as in nature we can have molecules that are left-handed or right-handed, sometimes we can characterize or describe fundamental particles as left-handed and right-handed. And this happens precisely with quarks. Quarks, they have a quantum number. I mean, they transform nicely under this symmetry. Okay, and this symmetry is a classical symmetry of the Lagrangian. The question now is this symmetry anomalous or not? Well, not always. It depends on this coefficient here. There is essentially a sum over the charges of the particles in your theory. If this coefficient vanishes, then the symmetry is there, and there's nothing new. But if it doesn't vanish, then the anomaly. One important thing about symmetries and anomalies is that, as I said, for each symmetry we have a conserved associated current. For the current transformation, we have these two, the vector and axial currents. And these are the ones that are produced in the materials. And if the symmetry is anomalous, these currents are no longer conserved. Okay? What else? Yes. Okay. Now there is something remarkable about this phenomena, and this that even though anomalies are something intrinsically microscopic, our description is based on just single particles and these kind of things, they can give rise to macroscopic phenomena. For instance, these that I just mentioned here, the Chiral Magnetic, Vortical, and separation effects. I will only focus on the Chiral Magnetic effect, which is the one we are studying and which is the most relevant to us. Because, as I said, it will be generated in the Quark Gluon plasma because quarks are chiral and we have this anomalous chiral symmetry. Okay. Intuitively, what is this chiral magnetic effect? Well, once again, from kindergarten, you should know about Ohm's law. That is that if you have a material with charged particles and you apply a magnetic field, an electric field, then you will get a current, okay, an electric current. This is from very old physics. Now the chiral magnetic effect is the same thing, but instead of with an electric field, with a magnetic field. Now you might wonder why this is something new, if it looks so trivial. Well, the thing is that for this current to develop, you actually need this anomaly. You need to have chiral particles in your material, and this is not what happens in our daily materials. Okay, and it was classically forbidden by the symmetries of the theory, but now that we get quantum mechanics into the game, we can have this kind of transport. Now there are two things we need for this current to develop. The first one is a magnetic field, and the second one is chiral imbalance. And this is, here I have a picture to more or less understand it intuitively. If we apply a magnetic field, the chiral particles will either align or anti-align their momentum with this magnetic field. Actually, left-handed particles will anti-align and right-handed particles will align. So we will have a movement of right-handed particles towards one direction and left-handed towards the other. Of course, if we have the same number of left-handed and right-handed particles in our system, we won't see any current. The net value will be 0. This is why we need chiral imbalance. We need more left-handed than right-handed particles, or vice versa. And this, at the end, gives rise to this current. Now, this current can be computed using several techniques, and this is what we find. And surprisingly, it is proportional to this anomaly coefficient that I was mentioning just before. So there is a correlation that if we have anomaly, then this coefficient is different from zero, and we can have this anomalous transport. Whereas if we have no anomaly, there's no way that we can get this chiral current. Okay, this is why we call it anomalous transport. I think one of the most interesting features of this current is that it is non-dissipative. Like intrinsically, the theory tells you this current cannot dissipate, and there are several ways to see. For mathematicians, you can tell them the current is topologically protected, or maybe you can think of the transport coefficient as being even under the T symmetry, under time reverse. Anyway, the thing is that it's non-dissipative, and this can open a door to applications. This chiral magnetic effect has already been measured in some materials, like this was the first one, zirconium tellurium 2. Now it has been measured in some others. Okay? But it has not yet been measured in the Quark Gluon plasma. Well, they are trying to. The chiral magnetic effect is at search at both LHC and RHIC, which are two different particle accelerators. And they already have some preliminary results they showed some years ago. And there is some tension, there is some discrepancy, because in the LHC they claim that they see nothing. There is no chiral magnetic effect whatsoever. Whereas in RHIC, they say that they obtain a signal that cannot be explained with anything else that is not chiral magnetic effect. And this is surprising because LHC works at higher energies than RHIC, and so naively you would expect the signal to be more intense at LHC than at RHIC. There are some experimental efforts to bring those results into agreement, but maybe it is not possible, and we have to resort to the theory. And this is, in some sense, this is what in my thesis I'm trying to do. One of the projects is to give an explanation to this, and we will see at the end of the talk one of the reasons of this, one of the possible reasons of these discrepancies. Okay, perfect. Now, of course, you may ask if we know. I mean, if this chiral magnetic effect for sure should be at the Quark Gluon plasma or not. Remember that we needed two things for the chiral magnetic effect to develop. The first one was the magnetic field, and this is trivial. Like if you have charged particles moving, you will generate a magnetic field. So this is there for sure. The thing that is more tricky is the chiral imbalance, because initially you will have chiral balance and you will have to find some method to induce chiral imbalance into the system, but the system is not interacting with anything. The thing is, there are some mechanisms proposed. I don't think they are very well understood, but there are reasons to believe that there is also this chiral imbalance in the material, so we should look for the chiral magnetic effect. Okay? So now we have the physics of the thing, we have a problem in mind. Let's see why we need holography to study. I mean, what are the ways to study the Quark Gluon plasma? The thing is, the Quark Gluon plasma is a very complicated thing, because it has been observed that it is strongly coupled. And we have a problem with strongly coupled systems because in quantum field theories, we only know how to compute things perturbatively. At least analytically, we only know how to compute things perturbatively. And this means that we only know how to compute things that are weakly coupled, that do not interact much, they don't talk much to each other. The Quark Gluon plasma is strongly coupled, so we have to forget about analytics from the very beginning. So there are some methods to study strongly coupled theories, as for instance the lattice. Essentially, in lattice methods, you just discretize space-time, and you can make sense out of the path integral prescription that otherwise is very complicated, and you can compute things. The problem here is that if you want to model the Quark Gluon plasma, you need to include many particles in the system, and you will very quickly exceed the computational capacity of your, okay? And the other thing is that in lattice methods, you won't be able to simulate real-time physics. And this is very subtle. I'm not going to explain why. But if we want to study how the current develops over time, or how it evolves, or how it relaxes, that is not an option. There are also some non-equilibrium quantum field theory formalism, but they are very complicated. You should avoid them in general. So holography seems to be the best alternative, and now I'm going to explain why. Okay. So first of all, what is holography? Holography, roughly speaking, is an equivalence between two very different kinds of theories. On the one hand, we have a theory that contains gravity. Essentially, it's a universe that is called anti-de Sitter, and this has to do with the curvature. It's an hyperbolic, I would say, yes, universe. And on the other side, we have a quantum field theory that is a scale invariant. This is that we call conformal. It means that it doesn't matter the scale at which we look at the theory, it always looks the same. So we have a conformal field theory in one dimension less. So if you were to imagine that all our theory lives in this disk, then the gravity part, the universe, would be the inside of the disk, and the conformal field theory would live in the boundary of the theory. Okay? And this is how we make the equivalence a bit more precise. And now what do we mean by these theories being equivalent is that anything that we want to compute in one side, we can compute it in the other, or we should be able to compute it in the other. Okay, and this applies to everything, to operators, states, correlators, dynamics, dimension of the Hilbert space, what else, the symmetries on both theories, everything. Now, there are several versions of this conjecture, because it is a conjecture, it has not been proven mathematically. There are some examples that have been found to work, but there are no proof, and we're far from having a proof of that. But there are strong evidences that it works, okay? So the strongest form of the conjectures says that both theories are completely equivalent. It doesn't matter if you are strong with coupling, if you have more or less colors, whatever. And now you can take certain limits and reach weakest form of the conjectures, which are actually better established. And the one that is of interest to us is the weakest, which is also the most useful one. Because the weakest form of the conjecture tells you that when one of the theories is strongly coupled, the other one is weakly coupled. And now you see why holography is so useful to us, because the Quark Gluon plasma is strongly coupled, and we don't know how to compute things in a strongly coupled system. But if we can map it into something that is weakly coupled, then we can compute things, okay? And this is where the strength of the conjecture comes, of course. Now, this very simple setup that I was talking about at the beginning of having a conformal field theory and de Sitter, well, having a conformal field theory is very restrictive because the Quark Gluon plasma is not scale invariant. We would like to have a normal quantum field theory. And this can be done, we can do some generalizations, and the price you have to pay is that now the universe that you have is not anti-de Sitter, but only asymptotically anti-de Sitter. Okay? And the last thing is that we want to put the Quark Gluon plasma at finite temperature, not at zero temperature as we are used to. And for that, it's very simple. In the gravity side, you only have to include a black hole in the inside, and the temperature of the black hole is exactly the same as the temperature of your conformal field theory. Now I have said that both theories are completely equivalent, that anything that on both sides and you compute have to match. But there is one question you may have, and it's about the dimensions. What about these dimensions? Why there is one more dimension in the gravity side? What is the interpretation of that? Well, the thing is that this radial direction, also called holographic direction, can be thought of or can be linked mathematically to the energy scale of your conformality theory. So that at infinity, at the boundary, you will have the ultraviolet of the theory, you will have high energy, very high energies, and as you move towards the interior, towards the bulk that we call it, you will flow to the infrared. Okay, so this is more or less the general idea of holography. We have seen why this is useful. Actually, when one is using holography, one always have in mind this holographic dictionary that we use all the time that relates things on one side and on the other. See, you have d+1 dimensions in gravity, are the dimensions of quantum theories. The radial direction, this is what I have just said, is dual to the energy scale of the quantum theory. The strongly coupled is dual to the weakly coupled, and vice versa. So for us, we want strongly coupled quantum theory and weakly coupled gravity. Weakly coupled gravity is just Einstein gravity, is general relativity, essentially. Strongly coupled would be string theory or whatever quantum gravity is, okay? And the last part of the dictionary is the thing that is going to tell us how to compute things. So we know that in our quantum field theory, we want to have matter, so we will have an energy momentum tensor, and this energy momentum tensor is dual to the metric tensor in gravity. So essentially, the metric tensor is gravity in itself, okay? And also we have two conserved, well, not so conserved currents in the quantum field theory, which are the vector and axial currents associated to the chiral transformations. These are the currents we want to study. We want to see how they evolve. This is the chiral magnetic effect, essentially. So what this is telling us is that if we want to compute the evolution of the currents, we need to include some gauge fields. Fields for our physicists are sort of synonyms of particles. Okay, we have a field for the electron, a field for the photon, a field for each particle. Gauge fields are interaction particle fields, but okay, we don't need to know this. So now finally, let's move to the to bring both things together. We want to study the chiral magnetic effect using holography. And for that, we follow a bottom-up approach. This means that we are not going to deduce the model from anything. We're just going to cook it up. So as I just said, we want to have matter in our quantum field theory, so we need gravity. This is this part here. This is the action, and this is the Lagrangian. This is what encodes all the information of the system. From here, we will deduce the equations of motion, and we will get all the information that we need. Okay. So, as I said, we want to have matter in the quantum field theory, so we need gravity here. And this gives the anti-de Sitter solution. The other thing we need is the two currents, okay? One for the axial part, one for the vector part. As I just said, for that we include two gauge fields, which are abelian, and this is this part in here. But in here, the symmetry is not anomalous. To include the anomaly in holography is a bit intricate, but suffice it to know that we have these kind of terms, which are called Chern-Simons terms. Okay, and that will be it. We have the action, the Lagrangian, we compute the equations of motion, we solve for the fields, we find the current, and we extract conclusions. Okay, there is one more thing we can do, and this is in view of having a more realistic scenario, especially if it's not so relevant for the Quark Gluon plasma, but it is if you want to study the chiral magnetic effect in some materials. Okay, those materials are not perfect; they have some impurities. In these impurities, essentially, will give you dissipation, and in this perfect model, there is no dissipation. So to include dissipation, we simply break translation symmetry. There are several ways to do this, and the simplest one is by including three scalar fields with simple profile. Okay, the difference is that you will have this k parameter floating around your equations. So this is it, and now we have to include some boundary term to have a well-defined variational problem. This is a mathematical subtlety that we don't care about. And then there is this last part, SNF, which is something we add by hand. And this has to do with the system we want to, with our setup, with how we're going to study carbon. What we're going to do is we're going to start from some equilibrium configuration. We'll have the currents at equilibrium. And we will drive by hand the system out of equilibrium. And this will be done by these external sources, S and F. So we drive it out of equilibrium and we see how it relaxes and what information we can obtain. Okay? So we find the equations of motion. They are very complicated. Nobody can solve the full equations analytically and sometimes not even numerically. So we propose an ansatz. This is that we write down a solution parameterized in terms of some functions, and then we solve for the functions. Now in this setup, we're doing a perturbation theory in the magnetic field. This means that we're only studying small magnetic fields. And this is a bad model, okay? I don't know if I said it, I think I did, but in the accelerator, in the LHC and RHIC, the energies are very high, and so is the magnetic field. The magnetic field is very intense. It's of the order the mass of the pion squared, okay? So why are we interested in small magnetic field? Because it's simple. This is a very preliminary study. Actually, nowadays we're working on generalizing this setup and including an arbitrary magnetic field. But for the moment, we are only able to study small magnetic fields. So we put the equations of motion. With the holographic dictionary, we compute everything we need in the Quark Gluon plasma, chemical potentials, temperature, etc., etc. And we solve numerically. And finally, we find the currents. And we study how they behave once they are thrown out of equilibrium, depending on the parameters of your theory, etc. So this is the current, the usual current we have in our daily lives. This dashed line is the equilibrium situation, and these color lines are the results from the out of equilibrium simulation. Here we study the dependence with how abruptly we drive the system out of equilibrium. So intuitively, if you drive the system smoothly out of equilibrium, it will have time to equilibrate at each time step. And so one would expect that the evolution of this current follows very closely the equilibrium evolution. And this is for big taus, we observe precisely that it goes very near equilibrium. And if we do it abruptly, well, it deviates more and more from equilibrium. What is relevant here, what you have to, or what we care about, is that there appears a delay that it depends on tau, also depends on the other parameters of the theory, which means that once you perturb the system, the current does not immediately build up, but it takes some time. And this is what might explain why they see the current magnetic effect at RHIC and not at LHC. And this is because the magnetic field is very short-lived. And the time life of this magnetic field is inversely proportional to the energy at which we are. Okay? So remember, at LHC, they are much higher energies, and so the magnetic field will be very short-lived, whereas at RHIC, it will live a bit more. And if there is this kind of delay, it may be the case that at LHC, the magnetic field does not live enough to produce the chiral magnetic effect. Okay, this is the key of all this business. We can study also how the current evolves with these impurities, with concentration of impurities. k equals 0 is no impurities, and we increase, we put more and more impurities. There is a transition between two behaviors, one in which the current goes down and then bumps a bit up, and the other one where we have monotonous decrease. Now, this can be understood in terms of the quasi-normal modes of the system, which is a bit more complicated, but we have a model for that. And you see also here that there is a time delay, that depends on k. We can repeat the same analysis for the axial current. We get some other curves. Now, when we have no impurities, the final equilibration value is a bit different because there is a contribution that does anticipate. But okay, this is not important for us. We can see the delay. And similar, this is for the energy current. Of course, if we don't have any impurities, there is no dissipation. We don't lose any energy. We don't lose energy at all. And as we increase impurities, we start losing energy. Okay. This is the time delay dependence, just for you to see it. This is with the quantity parameter. Here we have abrupt deviation from equilibrium. Here we have smooth deviations. And similar here. Here we have no impurities. Here we have a big concentration of impurities. And we see that we always have a delay, more or less, but we always have a delay. This might be at the core of the explanation I was talking about before. So this is essentially it. Let's summarize a bit. So first of all, we have seen that chiral anomaly induces a novel macroscopic, non-dissipative transport phenomena, as for instance the chiral magnetic effect. This chiral magnetic effect is a current search at LHC and RHIC, and there is some discrepancy between those. Now, on the other hand, we have concluded that holography is a suitable tool to study non-equilibrium quark gluon plasma. Of course, holography will never tell you the perfect right answer, the perfect quantitative answer. And this is because if you want to describe the quark gluon plasma, you need quantum chromodynamics. And if you want to do it via holography, you need to have a gravity dual to quantum chromodynamics. And this is very complicated. There have been some attempts. Some theories give you right answers for one questions, but not for others. So this is very complicated. So what we do here is we use a toy model, say, very simple model, with the basic ingredients we need, and we hope that the results fall into some universality class, and you get, for sure, you will get qualitative agreement, and if you are very lucky, you will get also quantitative agreement. But okay, this is beyond the scope of the project, definitely. And finally, we have seen that the delay observed in the simulations might be the reason why we observed the chiral magnetic effect at RHIC and not at LHC. And of course, what we're doing now is generalizing all these model. We can include time-dependent charges. We can include the intense magnetic field, or even time-dependent magnetic field. This will be like the full picture, even though time-dependent magnetic field is a nightmare and nobody wants to do that. But at some point we will have to deal with that. And that is essentially it. These are the papers I'm based on, mainly this one and mine. He's already in the archive. And that's it. Thank you very much. If somebody has any question, just feel free to ask, unmute, or whatever.
Hello, can you hear me? Can you hear
Yes.
me? Okay,
Yes.
sorry, I was having problems with my own audio. So
Okay.
Sergio, thank you very much for the talk. I hope it's been a little bit that everyone has like understood more or less what is the aim of your research and your PhD thesis, and I'm not sure if anyone has any questions. Just to like, just for my own curiosity, you've said that like there's this discrepancy between LHC and the RHIC experiment, and that is due to the this delay in the simulation. But is it due to the delay in producing the simulation, or is it due to the lifetimes you've said about the particles that you mentioned that is inverse to the strength of the magnetic field? Like I'm not sure that has been clear exactly. Where does the discrepancy come from?
Okay, the discrepancy, of course, they don't know where it comes from. One of the reasons we propose is it has to do with this delay. So, okay, we have that the magnetic field is responsible for the chiral magnetic effect. Now, the magnetic field dies very quickly, and the lifetime of this magnetic field is inversely proportional to the energy. So at LHC, that we have more energy, the magnetic field will be very short-lived, whereas at RHIC, they work at smaller energies and they have a older magnetic field that lives more time. And so the thing is that because we are out of equilibrium and we have seen that there is some delay, this means that if you apply a magnetic field, the system will not immediately respond. Apply a magnetic field and you will have to wait some time until the chiral effect develops. But it may happen that if the magnetic field dies before that, then no current is produced at all, and you would not expect to see anything.
Okay. Okay. I don't think anyone else has any question, but well, I'm just gonna thank you again for the talk. I think it was very cool, and thank you again for coming to speak to us about this and everything else. So, well, thank you everyone else for coming to the seminar. Our next seminar is going to be, I think, in 2 weeks' time, so the 30th of October. We already have a speaker, so we'll send you an email with the details about the talk, and we hope to see you all there.
Okay.
So, goodbye then.
Bye.
Have a good weekend, everyone. Bye.